Hi, my name is Mischa Dohler. I work for France Telecom R&D, and I'll present you in subsequent hours the tutorial on wireless cooperative communication networks. I'll expose you to techniques which are applicable to cellular, ad hoc, and sensor networks. These slides had been developed together with my colleague Aghvami from King's College London and presented in parts at WCNC in Hong Kong and ICC in Glasgow. Before I start the tutorial, let me just expose you a few application scenarios of the distributed cooperative topologies, one of them being the UMTS or alternatively WiMAX capacity and coverage extension. Imagine a cellular rollout with base stations covering a large part of the country and a few mobile terminals scattered all over that coverage area. Do imagine that a few mobile terminals are actually out of range of these cells, such as that laptop right here. Now what we could imagine is we use a mobile terminal at the cell edge to relay in a cooperative fashion the data to that terminal out of range. Alternatively, we could also use a distributed scenario where imagine the base station broadcasts the signal just as right here, broadcast it to the mobile terminals, two of them pick it up, and in a distributed space-time coding fashion relay the data to a terminal out of cellular range. Now the first method is known as ODMA, the Opportunity-Driven Multiple Access, which had been initiated by Vodafone about a decade ago. That concept here is fairly novel and requires distributed cooperative protocols to be run on top. Here you see a picture of a cafe in London. Here's Professor Aghvami just going into that cafe, and that cafe happens to have a wireless LAN access point. Now in London, there are quite a lot of wireless LAN access points, and one can imagine that one day there will be a complete coverage of central London using exactly these type of relaying mechanisms. What we could imagine is the two users sitting here having a coffee, browsing the internet, one being here, the other one being here, pick up the broadcast signal sent by the wireless LAN access point, and in a distributed cooperative fashion relay that maybe to Hamid and maybe to somebody else down the road who has a PDA and requires some spatial information. That service is also currently being tested in our Orange's unique service, where basically you are at home, you're entering your home, and you enter your wireless LAN access area, which at home in France is called the live box, and you then get access to that live box and have your phone calls automatically routed via the live box. You therefore initiate a vertical handover from GSM to wireless LAN. Now one day you can imagine that you would use exactly that unique service to relay data to somebody down in the road to facilitate also these type of services. Sensor networks is a really hot and emerging area, and here you see the example of sensors being rolled out in a forest. They might be rolled out just from an airplane, therefore randomly scattered all over the forest, and they need to report certain things, for instance fire, humidity, temperature, etc., and that data is collected either by a mobile or a fixed supervisor. Now, as it turns out, loads of people today try to optimize and actually try to maximize the lifetime of a wireless sensor network because, as everybody knows, these wireless sensors are very constrained in energy. As it turns out, unfortunately, the battery life of these sensors is limited, meaning no matter how much you optimize or maximize the network lifetime, if you manage to have algorithms on top which run for 20 years or 25 years, that will be of no use because your battery is likely to die after 10 years or 15 years. Therefore, one of the paradigms we need today when we design these type of networks and we also design them from a distributed cooperative point of view, you do not need to maximize lifetime. You need to optimize it for a certain period of time. Let's say you need to optimize your network's lifetime so that the network runs for 15 years. Another problem which you have with wireless sensor networks is that the startup phase requires a lot of energy, and therefore you need actually to have protocols in place which facilitate a very fast, very low energy startup of that type of network. And of course you can imagine that having distributed cooperative protocols on top will cost even more energy. Therefore, there are conditions when actually cooperative communication networks will not be beneficial because they need more energy. But as has been confirmed by a company we work with together called Coronis, which is a French company, the first one in the world to have rolled out more than 1 million sensors and actually make money out of that, they confirmed to us that the problem today is actually reachability. So therefore, maybe it is not the prime problem energy as such, which of course is also a problem, but one of the major problems is that their sensors are just not hearing each other. So therefore, having a distributed cooperative system in place would facilitate exactly that. Another example are unmanned aerial vehicles, where you would have a cluster of sensors here in a certain area which transmit wirelessly their data to an unmanned aerial vehicles cluster. These perform some form of cooperation and then in a cooperative manner transmit that down to either some receiving clusters or to some processing units. Now these UAVs could use beamforming or space-time codes or multiplexing techniques. Although this sounds very futuristic, this example, ironically, is the only one which is currently up and running. You're welcome to consult reference number 4. We have a design dilemma here, and that is very clear because these type of networks have basically a very, very large degree of freedom. That has triggered endless white papers, conference and journal publications. For instance, I did a search just very recently, and I found more than 500,000 references on that area, whereas in 1999, when I started working on that, there was not even a handful of publications in this area. So therefore, before I start that tutorial, and I always ask these questions to the audience, is it really worth working in an area which is so well explored? And if it is, don't we follow the same mistake which ad hoc networks actually did for several decades, that loads of people spend loads of effort to produce protocols, physical layers, routing protocols, etc., etc., and actually up to date there's no viable commercial product on the market? I'll leave these questions to you and to ponder about them. Now, as for the tutorial emphasis, of course a lot of materials are there. I had to cut down, so I concentrated on material from 2006 and from this year 2007, and since you're likely to have a very, very different background, I just give you a feeling for all the available techniques. My aim is not to go into mathematical details, but just to give you really a sufficient overview. So ideally, you should use your ideas, your knowledge to produce something viable in that area. I will start with some preliminaries. We will move on to hardware issues where I'll explain what kind of topologies are actually feasible, architectures are feasible from a hardware point of view. We then discuss channel characterization because, as it turns out, the wireless channel is very different from a traditional point-to-point channel. We then discuss transparent and regenerative physical layer algorithms. I've split both because both contain a lot of material, so therefore we will choose to talk about these separately. In the 6th topic, we'll talk about medium access control and cross-layer design, and finally we will conclude and give some ideas on the road ahead. You're welcome to download all these references which I cite in my from my personal website with a web reference given below. That will allow you to view the references in parallel to the tutorial. Let's move on to part 1, the preliminaries. I'll give you some useful definitions, so just really every listener is at the same basis as we are. And we will start with the infrastructure. And be it physical or logical, an infrastructure-based system is a system where the infrastructure is available prior to deployment, for instance in cellular networks or in wireless LAN networks. An infrastructure-less network is where the infrastructure does not emerge at all, or it emerges after deployment, such for instance as in the case of ADAC networks, where a virtual communication structure is built after the nodes have switched on. You can manage such infrastructure in a centralized manner as we do, and from France Telecom's side, such as here given the cellular network, or in a decentralized manner, such as for instance in a wireless LAN mesh network. You shall note that you may have a decentralized infrastructure-based system, for instance, you may have a decentralized radio resource management running, or you may equally have a centralized infrastructure-less system where you have, as I mentioned before, some clustering or some virtual structures running in the system. The information flow can be fourfold. You can have a point-to-point information flow. That means I'm talking directly to somebody. You could have a point-to-multipoint, meaning I'm talking to an audience. You could have a multipoint-to-point. A good example is if you have a choir singing to a single person, and you could generally have multipoint to multipoint. An equivalent example would be you have a choir singing to a general audience. You can realize these flows either by means of the direct link given just down here, or you can facilitate relaying. That means you have a direct link, but you also have a relaying node relay this information to my destination. Or you could have relaying stages where I have a source, I have a destination, and the information passes from source to destination via these relay stages, where the data passes more or less at the very same time, and some form of cooperation can happen in these relaying stages. A node could expose egoistic behavior, which is traditionally the case today. So we have two nodes in the cellular network talking independently to a base station. They could be of supportive behavior, meaning a node may just help another node to get its data relayed to the base station. Or we could have a truly cooperative behavior where two nodes help each other, so that is a true mutual help to get the data to the base station. As for the varying relaying methods, I'll give you some canonical relaying methods. More methods are out there, and they are often called differently, but I have chosen to split them into two different forms. One is a transparent relaying, the other is a regenerative relaying. The transparent relaying means that neither information nor waveform are modified. That means you only can do power scaling and or phase rotations. The terminal receives a certain signal, amplifies it, phase rotates, or does some other transformations with it, and amplifies and sends it out. For instance, we have the amplify and forward, in short AF relaying protocol, where exactly my terminal simply receives a signal, amplifies it, and transmits it. The signal remains analog. In the linear processing forward, the LF protocol, the terminal receives it, phase rotates it, amplifies the signal, and transmits it. In the nonlinear process and forward NLF protocol, you would have a nonlinear processing at the transmitter but relay the analog signal to the destination terminal. Then you have the class of regenerative relaying, and here we modify information bits or waveforms, that means the samples, and that requires clearly some much more complex baseband operations. And examples are, and they are not conclusive, you have for instance the estimate and forward, the EF protocol. You would detect the signal and then you would forward the estimated signal. You could also have the compress and forward, where you detect a signal, you compress and estimate it, and send it out. Then you have the decode and forward, which is well known. You would detect it, you would decode it, whatever decoding system you have used, and you would re-encode it, potentially using the same or a different code. Then there's the Persian forward, the PF protocol, where you aim at eliminating interference at the relay prior to sending it out. And then you have more sophisticated protocols such as the aggregate or the gather and forward, the GF protocol, where you perform some source coding and also potentially some compression before you send out the data. Let's move on to the key milestones, and these are really first key milestones, and apologies if I've omitted your contributions here. But it turns out that surprisingly already very, very early contributions emerged from Moylan in 68 and Coe and Gammel in 79 on support of relaying protocols from a purely capacitive point of view. These type of protocols have been picked up in 1996 with the 3GPP ODMA group, and later on analyzed in 1998 from Andy Nix from Bristol, which is a paper quite lost in space and time, but quite an interesting contribution and an early contribution in that area, showing the benefits of that type of supportive relaying protocols. The cooperative relaying, where really terminals help each other in a cooperative fashion, has been commenced in 1998 by Centonaris and in 2008 by Lahnemann. The purely distributed MIMO, where you really use distributed space-time coding methods, has been commenced by myself in 2000 and then picked up later or in parallel developed by Lahnemann and Hunter in 2002, and in 2003 there was Gupta and Stefanov who published interesting codes. Just as a reference, MIMO contributions have emerged in 1996 from a capacity point of view, in 1998 from a code construction point of view. I give you here my PhD presentation slides from winter 1998-2000, where I've written in fairly bad English actually my idea of using or forming these artificially formed antenna arrays. The idea was to use exactly in hotspots where you have many users at a certain space competing for the spectral efficiency, the spectral space available, to form jointly cooperative entities to actually boost capacity and use the opportunity of having these antenna arrays there. So I proposed where in beyond these 3G beyond system, where spectral problems occur, that means in these type of hotspots, that means where the user density is very high, I propose to investigate how adjacent mobiles could be used to form a multiple antenna array. Initially, I called that an artificial antenna array, abbreviated at AAA, but I was told that abbreviation had been used, so I changed that later to virtual antenna array, and ever since that is known as the VAA, the virtual antenna array. Giving a little bit an early state of the art on various systems, relaying systems now. I have a few slides which I will browse through fairly quickly. You can pause actually your tutorial presentation to read in more detail what I've written here. But just to give you an overview, in 71, Moylan published an interesting relaying scenario which had been previously studied by Sato. That had been then further exposed and analyzed from a capacitive point of view by Coe and Gammel, and they used systems with and without feedback, but a purely Gaussian channel. As I mentioned before, the concept group Epsilon has then in the 1990s investigated how could that relaying system be used in a cellular concept, and this has been then extended by Centonaris, Erkep and Ajang. Really, in 1998, they have proposed an effective user cooperative protocol, and they have later on in 10 and 11 extended that to more sophisticated schemes. Lahnemann introduced the famous decode and forward and amplify and forward relaying schemes. He has analyzed it from various points of view, such as outage and throughput, and he introduced, and also in his PhD thesis later, the distributed space-time coding protocols. The milestone paper by Gupta and Kumar show that if you have a large network and you perform relaying, throughput actually scales as 1 over square root m log m, where m is the number of users. Lately, just for your information, Tse and other people have shown that this scaling law scales slightly different if you use form of hierarchical structuring, but that shall be just for information. MIMO systems in general had been analyzed from a capacity point of view by Teletar first and later by Foschini and Ganz also from an outage point of view, and more practical space-time coding schemes have been proposed by Foschini and Ganz. He introduced spatially multiplexing schemes, then Alamuti introduced a very neat low complexity space-time block coding scheme, which had been later extended by Taroch et al., who also introduced the concept of space-time trellis codes. The distributed MIMO systems had been introduced by myself within the mobile VCE. We have performed numerous internal studies, which has led to quite a significant pool of patents, and that had been backed by about 20 industrial members. And we investigated that list of things here. We investigated the downlink distributed receive diversity, downlink distributed general MIMO systems and cellular networks. We then looked at the uplink. We looked at distributed relaying systems. We then extended that to wireless LAN systems and generalized that to very general distributed relaying topologies, which has been analyzed also in my PhD thesis. Who else looked into the distributed MIMO systems? Well, Gupta and Kumar did from a capacitive point of view. They had shown that having these type of very sophisticated multi-user coding schemes, you get certain performance gains. Also later, Andrei Stefanov and Elza Erkip looked into how could I design optimum distributed space-time trellis code, and that had been picked up today by many authors, and many new interesting and exciting contributions emerged in that area. Let's move on to some design challenges for these type of distributed cooperative topologies, and I like to present you that type of slide. This is how we see how the system design should be done. It's a fairly complex process, but if we do have an idea here in France Telecom, we usually look at the business case, at the services, at the capital expenditure and the operational expenditure, which CAPEX and OPEX stands respectively for. And once there you get green light, you look, all right, what kind of requirements do we have? What type of scenarios do we have to envisage? What kind of channel models will come out? What are the maximum transmission powers, etc., etc. That is also enveloped actually in terms of performance analysis. So you look, what is the capacity of your system which you are analyzing? That means what is the maximum throughput you can gain no matter how you tweak the protocols and the algorithms at the physical layer. We also do some link and system level analysis, meaning system analysis, you look really how does the entire system behave, how does it scale with users, stability, etc. Formal verification is a very interesting concept which I've been exposed to very recently. That has been used in industrial automotive industry already for quite a while, for instance in the Airbus industry, where you would make sure that the algorithms you put on top of your hardware work really with 0% failure. That means these formal verification tools go through every possible state of your hardware, of your protocols, of your software, and they make sure it works under all conditions. A good example is if you have a wireless sensor networks running out there reporting fire alarms, you want to be sure that no matter what happens out there, that if a fire occurs, these nodes will report that fire to the processing unit. So we are using in the national project, I'm leading a French national project which is called ARESA. We are using partners who do exactly that formal verification on the algorithms we develop. Now, once you have green light on the requirements and the performance analysis, you start looking into algorithmic design, meaning you look into physical layer analysis, into medium access control design, network protocols, applications, middleware, etc., etc. In parallel, you should do hardware design. You should design suitable microcontrollers, memory, amplifiers, buses, etc., etc. You name it all. Again, now a few example challenges. I'll browse fairly quickly through these slides. You're welcome to pause the presentation and read that very quickly. But from a business case, what we are really struggling, what everybody is struggling, is to find some commercially viable services out of these type of topologies. We believe we have some, particularly for the unique service, which Orange is going to roll out in November 2007. What you also need is some good billing mechanisms, because the question is open. If you support a certain user, how does he thank you? How does the network thank you? So you need incentive schemes, billing mechanisms, etc. Also for the requirements, it's not very clear what kind of channel models should be used, because not many measurements are there. What is very interesting to have is really measurements on channels which are distributed in nature. We need really realistic statistical properties, be they temporal, spectral, or spatial, and then to work from there. In terms of capacity, many things have been investigated, many things are still open, and in particular what I think is very interesting are the later points here. Extend or find capacitive expressions for the case of imperfect channel state information, for the case where you use non-Gaussian codebooks, meaning you're using real modulation indices, meaning real QPSK, BPSK, and also what is still open out there, how do I use the capacitive insights to get a synthesis on the topology which you are investigating. A lot of things are also open from a hardware design point of view. For instance, question is open, how do you make sure that the protocols are well synchronized? You need very good synchronization mechanisms at the hardware level. You need to make sure that your amplifiers work well, because if you do have a cooperative terminal very close to you, he may simply saturate your power amplifier. You also need to make sure that if you operate in an FDMA type of fashion, that your filters don't spill over too much, not to block other bands, etc., etc. Algorithmic design, loads of things are well explored, but what is interesting are tangible cross-layer design issues, codes, and that is very interesting, codes which are robust to synchronization, channel estimation errors, feedback errors, etc. And also codes which can easily trade diversity gains, coding gains in throughput and complexity. And finally, because cooperative systems will inevitably be interference limited, we need novel and innovative interference cancellation techniques. At medium access control, we need optimum access strategies, interference mitigation and avoidance protocols. We need tangible cross-layer design protocols, and also a unifying framework for distributed MUX, a part of which I'll be explaining you later on in the tutorial.